Example 5. Use information about the values of f prime and f double prime, so the first derivative and the second derivative, to help us graph this function. So let's just take our derivative. So our original function is f of x equals x to the 2/3. Our first derivative is 2/3 x to the 2/3 minus 1, which is minus 1/3. And our second derivative is equal to, I'll do it in steps. 2/3 times minus 1/3 x to the minus 4/3, because again, I'm going to subtract 1. And this is equal to negative 2/9 x to the minus 4/3. Now, remember, basically what we need to do is we need to find out when things are positive and when things are negative and when things are 0, right? So let's talk about f prime. F prime of x equals 0, never. Because this is really the same as 2/3 times the cube root of x. And x can't be 0 because it can't be 0 in the denominator. So we know it's not 0 anywhere, but is there a place where it goes from positive to negative? Well, since it's a cube root, it does. And whenever x is negative, so if here's 0, remember we definitely have an open circle at 0. But everything to the left is going to be negative. So our slope would be decreasing. And everything to the right would be positive. So everything would be increasing. I have f prime, and this is negative, and this is positive, and this is 0. Now, if we talk about the second derivative, that equals negative 2/9 times the cube root of x to the 4th. Now, x to the 4th is always going to be positive, which makes my denominator always positive. First, take that to the 4th power, which always gives me a positive value, but this whole thing is negative, which means the function is negative everywhere, from negative infinity to positive infinity. That means it's concave down. Now let's put this all together. All right, so I know I have a point at 0, 0, because the original function is x to the 2/3. So if I put in x equals 0, I get y equals 0. And also I can say this is 1, 1, and I can say this is negative 1, 1. So I know I have points right here. And I know it's from 0 to infinity, I know it's always increasing because it's positive. So, and I also know it's concave down. So it's going to go like this. And the same thing on the other side, except it's decreasing. So if I come from the left and go through that point, I can see this is always decreasing, and it's also concave down. And if we look here at what it's supposed to look like, we did a pretty good job. Sketching without an equation. Of course, graphing calculators and computers are great at graphing functions. Calculus provides a way to illuminate what may be hidden or out of view when we graph using technology. More importantly, calculus gives us a way to look at the derivatives of functions for which there's no equation given. We already saw the idea of this back in section 3, where we sketched the derivative of two graphs by estimating slopes on the curves. And here's a table, if you would like, you can summarize the data in a table that looks like this. This is the function, this is the first derivative, this is the second derivative. If the function's increasing, if I look at it, that means f prime of x is positive. If it's decreasing, it means it's negative. I don't think I agree with this, because you can't really get anything about concavity from f prime of x. But from f double prime of x, you can get that if it's positive, it's concave up, and if it's negative, it's concave down. When f prime of x equals 0, the graph may have a local max or min, which would be my critical point or points. When the second derivative, or f double prime of 0 equals 0, we have this, what's called an inflection point. An inflection point is where a graph changes from concave up to concave down, or vice versa. Example 6, a company's bank balance, calling it B, in millions of dollars. I'm assuming this is T, and I'm assuming this is balance, so I'll just call it B. T weeks after releasing a new product is shown in the graph below. Sketch a graph of the marginal balance, the rate at which the bank balance was changing over time. Anytime I see marginal, I think derivative. And what the first thing I want to know is I want to find out where my zeros are for my derivative. This is going to be, this is B of T. This is going to be B prime of T. And this is T. So I'm taking the derivative. If I take the derivative of a function and I set it equal to 0, I'll find my maximum and minimum values. So here I have a minimum value, and here I have a maximum value. So I guess we can say this is 0.5. And that looks like 3. So that means I have a 0 at 0.5 for my derivative, and a 0 at 3 for my derivative. Now, let's talk about the different intervals, because it's decreasing here and decreasing here and increasing only right here. So let's write this over here. It's increasing from 0.5 to 3. It's decreasing from 0 to 0.5 and from 3 to infinity. That means I have a 0 at 0.5. This is f prime of x. I have a 0 there, and I have a 0 at 3. It's decreasing here, so this is negative. It's increasing here, and it's decreasing here. Now let's do our double prime. I have what I call a point of inflection, because notice it's concave up here and concave down here. It's concave up here, which means I need 2 points of inflection, because if it's changing from up to down, there's got to be a point where it's 0. So if I were to draw that, it would be somewhere like in the middle right here. So we're going to say at 2, we have a point of inflection, and let's say 6. That means right here, it's going to start being concave up. We have our 2 points of inflection, and I know from 0 to 2, it's concave up, which means it's positive here. And I know from 2 to 6, it's concave down, so it's negative. And then from 6 on, it's positive. And I know from 0 to 0.5, it's decreasing, which actually means it's negative. If I were to draw a tangent line at 0, it maybe would look like this. It's very steep, so it's pretty big. And as I come around, I'm having to turn my ruler a little because it is curving. And right at the very end, it goes really fast to 0. That's what it looks like to me. Here I have a large negative number. And as I get closer and closer to 0, it becomes smaller and smaller. It's going to start out really big, and then it's going to get smaller and smaller. And then when it gets to 0.5, it's going to start increasing. So remember, we're graphing this function right here. Notice it's negative, and then it becomes positive. It starts out here at 0 at the minimum, and then it starts going, like at this point, it's probably like this. And at this point, it's probably like this. And then notice here, it's probably like this. So it's changing, but it's always positive, which means I have to go up above the line, but I have to come back to 0. It's increasing always, but the slope is getting bigger and then smaller. And then it's decreasing to infinity. So it's negative. It starts out with a larger slope. And then for this function, you can see that the slope is starting out small, then it's getting really big, and then it's getting smaller and smaller. So I would say it looks something like, and it's got to come up. Let's do this. Let's look at what's happening with the second derivative. So the second derivative is positive, which means it's concave down. It is concave down all the way to 2. This is all concave down. Then at 2, it's still increasing, but it's increasing more slowly until it gets to 3. From 3 to infinity, it's negative. And it's going to be concave down. And then it's going to be concave down till it gets to 6, at which point it's going to start being concave up, which is why it's getting smaller. This is a graph that you can say is a graph of the derivative of this. There's the original graph. If we want a more accurate sketch of the derivative function, we could estimate the derivative at a few points, meaning you could just draw these lines and you could find the slope of each one of these lines. If you want to find a more accurate sketch, what you can do is put a few lines in and take the slope, because the slopes are the derivative. So here I have a -10. This is a +3. This is a -1. And then they put it into a table. They said it's to 0.6. I said to 0.5. So we'll use 0.6. It doesn't matter. And these should be the same as what we got. And this tells our concavity are increasing, decreasing. And notice here, all right, so here's a line drawing of what our graph looks like. Remember, it started out negative. It went to 0. Then it went to a positive value. It came back to 0. Here it went to, I think we said 6. but they're saying 5.5, doesn't matter. And then it's getting less negative. Remember, because it's kind of, the slope is changing. So this is a line drawing. We had the right idea. Notice how we had a very negative slope. It's getting closer to 0 here. Then it's going positive. Then it's coming back to 0. I said 3. They say it's a little over 3. Then I knew it was coming down. I didn't know what the slope was, but I knew then it was getting smaller. So we had the right shape, even though we didn't have the numbers. We didn't figure out the values. Thanks for watching.